Hi, sorry about getting cut off before, but we were solving this problem. We're looking at the acceleration due to gravity in Mars. And when you calculate this out, you get 3.72 meters per second squared, which checks out because if you Google, the acceleration due to the gravity of Mars, it's roughly 3.11, 3.711 like that. So it's pretty accurate. So here's a way that we can actually see or calculate the acceleration due to gravity without actually being there if we know the mass and we know the radius. So this is the mass of the planet, usually. It could be a star, it doesn't have to be a planet. So the central object. And that's the radius. So it's the distance usually, but distance to surface of the planet or star, and of course that's also what we call radius, right, for the most part. And keep in mind that these must be in kilograms and meters to officially do that. Okay, so let's go back here, and that's where we are here. This is specific to Earth. Notice the E right here, and if you see that on homework or assignments and whatnot, RE refers to the Earth like that. Alright, so the last thing we're going to calculate is orbital velocity and relate that to Kepler's laws. So if you take a look here, we have the Earth and the Moon. And the Moon is making a circle around the Earth. In fact, what we can say too is if we were to draw, for example, let's go back here. We know that the Moon is being attracted to the Earth with the force of gravity, just as much as the Earth is pulling the Moon. But if we just isolate the Moon, so we're just looking at the Moon, so not the Earth at this point, we can see that the force of gravity is causing the object to move in the circle. It's causing the centripetal force. Because without the force or pull of gravity, this would just go in a straight line tangent. So what we can do mathematically is write that the force, the centripetal force is equal to the gravitational force. So let's go ahead and write that out. So I'm just going to redraw this because I want to make a very specific point because sometimes it's confusing. So this is not a great circle, but you get the idea. So the force of gravity points to the center of our circle that the Moon makes. And we set that equal to Fc, the centripetal force. So if you look at this calculation, you're going to see the force of gravity. It's going to be, in this example, I'm going to use the Earth and the Moon, but you can use this as a general example, so it can be anything, right? So G, mass of Moon, mass of the Earth, distance between the Earth and the Moon. So I'm just going to leave that as R, but remember R, I'll just put it in a different color. R is that distance. So it includes the Earth radius, the distance to the Moon, and the Moon radius. So that's what this R includes. Usually it's referred to orbital distances. So if you see orbital distances, that includes everything. So actually, I'll even write it like that, or orbital. Orb squared equals. Now this is mv squared over r, but the m here is going to be the object that goes in the circle. So m Moon, okay? Because this is making or moving in a circle. We're not going to put the Earth there. It's confusing because you have two masses. You want the one that's actually doing the circular motion. It's not the Earth. Earth is stationary in the perspective of the Moon. So mv squared over r, right? So notice that if we set these equal to each other, we can get the orbital speed. How fast is this going? So v is going to represent the orbital speed because orbit is basically the circle, if you will, and speed just tells us how fast. So let's solve for it. So notice that the Moon cancels the mass and one of the r's. So I get G, me, r, orb, equals v squared. In fact, I can, finalize this by taking the square root of g ME orb. So, of course, this is the orbital velocity equation. So what matters here is, you notice, is the mass and the radius of the orbit. So the mass of, I'm going to call it the central object. So it's Earth in this case, but it could be a star, it could be whatever the bigger object is. It's the central object. And the orbital radius. These are the factors that contribute to it. So if you are closer, it makes this number higher. So as you might imagine, the closer you are, the faster you're going to go. The further you go, the slower. What's a great example of that? If you think about the sun and all of the other planets, right? Mercury has a pretty fast orbit. But if you look at Pluto way out here, it's going to take much longer, right? To make that trajectory. So you can say the bigger the orbital radius, the slower it will go. Because if this number is big, then that number becomes small. And then vice versa, the mass of the planet. The mass of the planet gives you a faster velocity. So if I increase the mass of the Earth, I increase the force, which makes this go faster. So something that's not dependent is if you notice, the mass of the moon cancels, right? So that's pretty cool. So technically, at this distance anywhere, right, the R orbital, I could put a piece of garbage here. I could put like a cotton ball. It doesn't matter, the mass. That will also travel the same speed. Well, I actually have it drawn this way. That will travel the same speed around. So that's a really interesting thing. So we say the mass of orbiting object does not contribute to speed. Pretty neat, right? Sorry, so I got cut off somewhere here. So what we're going to do is take it from here. So I said M is going to be the one making the circle. So why don't we do this? We can kind of allude to what we're doing here. So what I wrote was G, M, moon, M, Earth, equals R, orbital, equals M, moon, V squared over R, orbital. And that's where I left off. So at this point, we can simplify this. So notice that the moon's mass cancels, and then this is squared. So this R cancels out one of those R's like that. So what I get is G, ME over R orb equals V squared. And you can see if I solve for V, I get this. So some of the implications of this include the following. So the velocity at which this object orbits depends on the mass of the orbiting, the mass of the central object, okay? So it could be the sun, it could be the Earth, but it's the central object. So in our example, it's Earth. And then R represents the orbital radius, so how far away. So if I make the mass bigger, this becomes much larger. So that's because the gravitational pull is stronger, and it will speed up the object. Radius is inversely, so if this number is big, this becomes small. So the example I like to show you is, Mercury versus Pluto, right? So Mercury goes really fast around the sun because it has a smaller R. But Pluto is way out here, right? Well, that's a big radius, which means that's going to be a slower velocity. So if you think of it that way, it should make sense. It takes, I actually don't know the exact value of how long it takes Pluto to go all the way around, but it's a long time versus Mercury. Now, the biggest thing you should get from this is that the orbiting mass does not contribute to speed. So watch what happened before, right? The moon, the mass canceled out, so it doesn't even come into our equation right here, which means that no matter what the mass is, as long as we put it at that radius, So I could put anything here. I could put a space garbage here. I could put a rock. I could put a cotton ball. I could put a rocket. Anything at this exact radius and that mass, it will have the same speed. So doesn't matter the mass here. So as you can see, mass of the orbiting object does not contribute to speed. So sometimes we use the word, instead of orbiting object, the word satellite. Satellite. I think I spelled that wrong, but that's okay. Satellite refers to the orbiting object. So it doesn't, a satellite could be the moon, because that orbits around Earth. It could be the space station. It could be space debris. It could be anything, as long as it's orbiting something. So if you see the word satellite, it doesn't necessarily mean what you think is a satellite, right? Like the little, of course, you know why that name is, hopefully now, is because it orbits the Earth. Satellites that are up there that control communications or whatever they do up there. Okay. So we got orbital speed. And there you go. That's me explaining how to do such a thing right there. And there we go. That's it in words. I'm going to skip this exercise for now, but if you have the radius and the mass, you can find the velocity. So the sun, orbital velocity on the surface of the sun. So in other words, if I were to be able to go around the sun right on the surface, the speed that I would have, which is, as you can see, pretty high. Wow, right? Okay, great. So now we're going to shift gears and talk about Kepler's laws of motion. So Kepler describes how planetary motion works, and he does it with 3 laws. The first law is the idea that all orbiting objects travel in ellipses with one of the central objects at the focus. So here is more or less what this is exaggerated here, so just keep that in mind. That the Earth is actually almost nearly circular orbit, but it's not perfect circle. And since it's not a perfect circle, we can say that it's an ellipse. So all orbiting objects travel in an ellipse with the sun or the central object at the focus. Now this animation's incorrect. I hope you notice that, because if you notice, when the object's close to the sun, it's going to have a stronger gravitational force than when it's further away, because ours are different. So, okay, so yeah, so this is what an ellipse looks like, where you have the sun and the planet. Don't worry about the terms right here. We're not going to cover those at all. But the fact that you have the object going faster here and slower here comes from the poles of gravity being different, and also comes to the next law of Kepler, which is saying that equal areas will sweep out in equal times. So in other words, if I were to calculate this area of this green triangle right here, and it took us 1 hour to go from here to here, then 1 hour from here to here, this area would also be the same. So that again has to do with the fact that the pull is stronger here, so you're going to go faster here and then slower out here. Let's see if I could show you this before the there it goes, before the video is over. So each tick is a second, and each area in the gray is the same. So that's what Kepler's laws say, and notice that when it gets closer, it goes faster. So Kepler's law, second law, says that equal areas happen in equal times. In the next video, I'll finish off the final video talking about satellite motion and Kepler's third law of motion.